Start recording. And then let me screen share on Discord as well. Okay, can everyone see my screen? Awesome. So hi everyone. For those of, I think most people here know who I am, but for those of you who don't know who I am, my name is Aiden. I am an applied mathematician. I'm an applied math grad student, so I'm pursuing the study of applied mathematics at a graduate school. I'm going for my PhD. And I'm interested in a lot of fields of math, but my main interest, the thing that unites pretty much all of my interests in math, is computation. So the point of this week is to basically put into words and into writing all the things that I think are kind of the most important uh, things to know from this field of math called approximation theory in terms of its applications to computation. Um, Generally speaking, approximation theory is just the study of taking things that are hard to understand and approximating them with things that are easy to understand. Um, you, if you work with computers at all, you do this, every single time. And I want to discuss kind of the most common um, approximation you do in computation, which is just the simple fact of floating point computations. Um, so let's, I guess, begin. Um, so we're going to start with a bit of something called information theory. Um, so there's to a computer scientist and to some other fields of math, the smallest piece of information that can possibly exist is called a bit. I claim you're actually all very familiar with bits, even if you haven't heard the name, though I'm pretty sure you have. It's just the littlest amount of information that you need to distinguish two things from each other. If I had two identical spheres and I colored one of them red, I would have added a bit of information. I would have added just enough information that you can distinguish the two balls and pretty much nothing else. So a bit can distinguish true and false. It can distinguish a 1 from a 0, positive and from a negative. Basically, any two classifications you can give something, me telling you that an object fits into one of them is a bit of information. Um, Now, the computer science has invented words for collections of bits. So a byte, which is, I think, a more familiar term, it's like the byte in kilobyte, um, is 8 bits, and a little piece of trivia, a nibble is 4 bits. It's half a byte. Um, so, I'm not going to get into information theory that much, but basically, from a practical standpoint, is like all information can be stored as bits. Um, and because we live in a world and we are constrained by things like, um, having finite amounts of memory in our computers, um, any information we want to store has to be stored as finitely many bits. We can't have an infinite number of bits lying around um, because actually that would create a black hole. But just little bits of fun with black holes. Anyway, now I'm going to assume that most people listening to this have a background familiarity in computer programming, at least up to the level of maybe having worked with some Lua before or some other programming languages. And so there are, a couple of data types that you are likely familiar with. And these are commonly stored using, or these are ubiquitously stored using bits, and there are some common amounts of bits that we often choose to store these things. So in theory, you could store any Boolean value in 1 bit. So you could store, a true false as a single bit. For what I will call in this talk weird technical reasons, Booleans are not often actually stored as a single bit, but in theory they could be. Often integers are stored anywhere between 8 and 64 bits. And the subject that we're going to be talking about most today, floating points, usually are either 32 or 64 bits. And a string is kind of any amount of bits within reason. There's not really a good guide on exactly how many bits a string is going to contain. So again, I'm talking about like 1 bit is enough to store the difference between true and false, and yet I'm saying that like we're storing integers using these number of bits. So that I haven't really explained exactly how one would go about storing an integer using only bits, but we'll get to that in a bit. Okay, so if you've taken any level of algebra, you probably have heard, well, you've probably heard the statement somewhere before that there are more numbers between 0 and 1 than there are numbers 0, 1, 2, 3, 4 onto infinity. And this is a true statement. There are a lot of numbers. And this presents a really big problem for computation. Because basically what we want to do is bits are really good at telling things apart, right? That's how I describe them. A bit of information is enough information to distinguish two objects. Okay, so if I only had 1 bit of information, I could tell you, whether something is 0 or 1. That would be a distinction I'm making. But now, what if I go to 1/2? Well, now to distinguish 0, 1, and 1/2, I would need an extra bit of information. I would have to tell you, 1/2 is not 0, and it's also not 1. So each of those distinctions would be essentially a bit of information. And so every time we add a number, we basically need more bits to store. Every time we add a number that in our list, of numbers that we're representing, we need more bits to distinguish them all. And there are an infinite number of numbers, so we would need an infinite number of bits. We would need to do an infinite number of checkings of are these things equal, yes or no? Are these things equal, yes or no? Is one way to think about it. So we need a better way of representing real numbers. And as I said at the start, we're doing approximation theory. Our whole goal here is to take something that's hard to understand or hard to deal with, in this case, the blinding mass of how many real numbers there are, and we want to approximate this problem with something that's well understood. We're going to do this using something called floating point arithmetic. But as well, the problem of representing real numbers kind of breaks down into two fundamental problems, and we're going to try and use some sort of representation to solve these two issues. Sorry, I got a bit ahead of myself there. The first thing is, right, real numbers can get arbitrarily big. There's that like old kids phrase where it's like, oh, what's like the biggest number you can think of? And someone says, 2 million, and then the person says, well, I can think of a bigger one, 2 million plus 1, right? So the real numbers go on forever. So there's this fundamental problem of how do we represent numbers that get like infinitely big? And then the other problem the real numbers have is between any two numbers, there is infinitely many numbers between them. This is called like density. The real numbers are very dense and they get very big. And so we only have a finite amount of information we can work with, so we have to figure out a way of approximating these numbers in a way that deals with both the increasing size of the numbers and the density of the numbers. And both of these constraints will require information. And so the floating point number, which is the general approach used to tackle approximating real numbers, tries to deal with these both by breaking these two bins of information apart. Actually, there are three bins. We have one bin that stores whether the number is positive or negative, another bin which stores how big the number is, and then another bin which basically deals with like the density. And these bins are called the sign, which is the sign bit, the exponent, which is the size, and the mantissa, which is the density. I do not really know a good reason why such a weird name was chosen for the density part, but that I think it's Greek. I don't remember. This brings. Sorry, what? Yeah, sorry, I said that out of order. The sign is whether it's positive or negative. The mantissa is the density part. So for instance, the exponent would tell you whether your number is like roughly equal to 0, roughly equal to 1, roughly equal to 2, roughly equal to 4, etc. And that roughly equal part is handled by the mantissa, if that makes sense. Oh, by the way, please, I do prefer, I like a lot of questions, especially, but it is hard to read the chat, so unmuting and talking is a good option. Or if you ask a question in chat, maybe Ethan could unmute and ask if you don't feel comfortable unmuting. But anyway, yeah, sorry. Yeah, the exponent to me makes sense as a name, but the mantissa, like, well, no one actually knows what the mantissa is until you learn what a floating point is. Okay. So this brings me on to my favorite slide name of all time, which is the IEEE 754 32-bit float. So there is this group called the IEEE. They are basically an international group of electrical engineers, and at this point now also computer scientists and computer engineers, basically all the kinds of people who deal with this kind of level of like how do you actually design a computer and how do you design standards that all computers can agree on. And these people sat down and they thought up a standard by which basically all computers now use to represent numbers. And this is the IEEE 754 standard. So almost certainly, like I would bet my entire life savings on the fact that your computer's CPU has dedicated infrastructure for computing and dealing with IEEE 754 floating point numbers. It is the most ubiquitous way of representing floating point numbers in the world. Now, there are two commonly used methods within the IEEE 754 standard for representing real numbers. One uses 32-bit and one uses 64-bit. The 32-bit is often called just a float or a single precision number, and a 64-bit float is almost always called a double, though for weird reasons in Lua it is called a float, and there is only one option, which is the 64-bit double. Technically speaking, you can go into your developer settings in Lua and change that, but unless you're doing that in Lua, you have just the 64-bit float. Now, in order to make my life easy, we're going to consider the 32-bit case because it's just a smaller number of bits. But the 64-bit case is kind of just a beefier version of the 32-bit case that has more information to work with. 32 bits is half the amount of information, so we're going to have a harder time approximating numbers, but it's also going to be more efficient. So we're literally going to break this down bit by bit. We got 32 bits to play with. Every single bit does a specific job. I told you specifically that a bit can distinguish between a negative and a positive number. And so we're going to dedicate one bit to doing exactly that. There's just one bit in the number whose entire job is to tell you whether or not that number is positive or negative. This can lead to some funny consequences. Within the IEEE floating point standard, there is a difference between positive and negative 0. Basically, there is a way of representing 0, and 0 doesn't have a sign. In classical mathematics, it's neither positive nor negative, but there's still a bit floating around whose entire job it is to tell you whether or not something is positive or negative. And so, depending on how you put that bit, you're going to either end up with positive 0 or negative 0, which, I don't know, that's kind of funny to me. And it's funny to some other people too. So then we allocate 8 exponent digit bits to determining how big the number is. So basically, you can think about it. So I have these 8 bits to play with, and we're going to use that to tell you how big the number is. So roughly speaking, an 8-bit, though those 8 bits can tell you, like, if it's all zeros, then you're between 0 and 1. If you have 0, 0, 0, 0, 0, 0, 1, then you're going to be between 1 and 2. And so basically you have these bins between 0 and 1, 1 and 2, 2 and 4, 4 and 8, 8 and 16, 16 and 32, 32 and 64, on and on and on. And these bits tell you which bin that's in. So they tell you, again, roughly how big your number is. And then we dedicate 23 bits, most of the floating point number, to determining where in each of these bins you actually are going to end up. So most of the number is going to this like accuracy thing of figuring out exactly where in the bin you are, and then 8 bits are going into telling you what bin you should go in. Is this making sense? This sort of bin analogy. Maybe I should draw it, which I guess I will do. What am I looking up? Paint. All right, let me switch my screen share. Yes. Yeah. So is the question why was that chosen? So that is a good question. The design committee basically, they released this whole thing basically outlining their choices and why they made them. My recollection is that, well, so again, the exponent basically determines how big of numbers you want to deal with, or that you can deal with. And so the choice for the mantissa really came down to not the mantissa, but the exponent. You're going to use 32 bits for this. You're going to use 1 bit for the sign. So as soon as they picked how many bits for the exponent they wanted, they were now they now had 23 bits left over for the mantissa. And the choice for an 8-bit exponent, I think, came down to the fact that that is an 8-bit exponent is the size of an unsigned integer with an unsigned 8-bit integer. An 8-bit integer, unsigned 8-bit integers were very common. And so not being able to I think that I can't remember, but I think that's basically the reason is because it was the size of an unsigned 8-bit integer, which is there's literally an entire type of game called an 8-bit game, right? And it's based on the fact that things were stored with 8 bits. So sorry, here's my. Can everyone see my bins? Okay, so basically, we're using 8 bits to determine which bins you're in. So like this bin here from 0 to 1 would correspond to all 8 bits being zeros. Because again, bits can be stored as zeros and ones, and so like this bin here corresponds to the all zeros bin. And then if I were to change this to a 1, we'd be in this bin. If I was to change this to a 0 and this to a 1, we'd be in this bin, etc. So we make these bins of various sizes, and we use the bits to determine what bin it is, and then we use the sign to determine whether it's positive or negative. And the bins are in powers of 2. So the bins go from 0 to 1 to 2 to 4 to 8 to 16 to 32 to 64, on and on and on, all the way to 2 to the 1. I can't remember. I have it written in my slides somewhere, but basically, these are the powers of 2, and those are the bin sizes. So it's this kind of interesting system, and then the mantissa basically says, okay, we know we're in this bin here, but where in this bin are we, for instance? And it basically subdivides the interval and tells you where in the subinterval you are. And notice how I drew this. I started by dividing the interval in 2, so it takes 1 bit to tell me which side of this interval we're in. Okay, then I subdivide it again. Now it takes 1 more bit to tell me which subinterval we're in. I divide it again, tells me which, each one of these divisions requires another bit of information. And so you just keep dividing the subinterval in halves, and that's how you basically get a number in that bin. And you can do that 23 times. So imagine subdividing this interval 23 times. You're going to get a very small bin at the very end. And so this basically, well, not basically, but this is how floating point representations work. Let me change my window back to my notes. So yes. And you can look online and find how many bits are being allocated for the 64-bit float. But again, we're just worrying about the 32-bit float for now. I hope by now most of you have run into scientific notation, because floating point representation can and should be thought of like scientific notation, right? In scientific notation, you have a number at the beginning that's always between 0 and 10, which has some number of digits, and that number basically is the mantissa. It tells you where in the bin you are, and then you have a second number. You have 10 raised to some number. That number is the exponent. The only difference is, with floating point, we're doing that with binary digits. So instead of representing things in base 10, we're representing numbers just as strings of ones and zeros. But it literally is scientific notation. It is some number that's less than 2 times 2 raised to some other number. Um, and thinking about it this way, actually, everything you ever learned in science class about like, oh, how many significant figures you have after a computation, like these may have seemed somewhat trivial, and if you're a computer scientist instead of a chemist, you may have been like, why do I even care about this? But it turns out everything you ever learned about scientific notation and significant figures carries over immediately to floating point computations. The exact same tools you use to understand significant figures in scientific notation, you use to understand significant digits in floating point representations. Um, Now, in this explanation of floating point, I have excluded some special characters. For instance, in Lua, there is in floating point in Lua, actually, and in the IEEE 754 standard, there is a specific number that represents infinity and a specific number that represents negative infinity. So these are just specific strings of bits that mean infinity or mean negative infinity. There's also specific strings of bits that mean nan. Nan is a floating point number, even though it's not a number, it is in a floating point standard, and so we have to dedicate some string of bits to mean nan. However, there are like 8 of these special things compared to the 2 to the 32 minus 8 non-special things. So those are exceptions, not rules. And so in general, this is kind of the correct way to think about things, as there's 8 exponent bits and 23 mantissa bits. But again, there are yes, there are some non-standard things that happen, but those are really there as safety nets for you. There's this great excerpt on Wikipedia from the main guy who designed this standard, and he was talking about how people thought like, oh, the inclusion of nan and inf and stuff was only for like the hardcore analysts. And he really pushed back on this because, if you're actually a really hardcore analyst, you don't necessarily need those guardrails, right? You don't necessarily need nan if you really, really know what you're doing and don't make mistakes. Things like nan and inf are actually around for when you do make mistakes. So they're there to help you not to be these weird edge cases. So just to point that out, it's not this like, the floating point standard was designed with care in mind and usability. So this has been a lot about like how we actually represent things, but let's talk a little bit about the approximation theory here. So this whole process of floating point construction has been a process of trying to approximate a real number. We broke the real number line into these bins that I drew in Paint for you using the exponent bits, and then we broke those bins into sub-bins using the mantissa bits. So at the end of the day, we are only able to subdivide that interval 23 times. So at the end, we won't be left with an interval. Sorry, we won't be left with a number. We will only be left with an interval. All we can say is that your floating point number, or say your real number, which you're trying to approximate with a floating point number, lies in some small bin that we know. And we just give each of these bins a name, namely as a floating point number. So really, when you're doing floating point computations, your numbers aren't numbers. They are intervals of numbers. A floating point number isn't the number 1. It's the bin around 1 of a specific size, which is something kind of interesting to think about. And so to kind of formalize this intuition, there are some notions in approximation that we need, namely absolute error and relative error. I found it kind of a hassle to remember these. I mean, it wasn't too hard, but I think there's an easier way to remember them, which is that absolute error is additive error and relative error is multiplicative error. And once you understand this, it becomes much easier to figure out what kind of error you want to use and how to use that kind of error when you're doing these error analysis type things. Um, so, as an example, suppose that there's some number y that we're trying to approximate, and x is our approximation. Maybe y is the square root of 2. Whenever you input square root 2 on your calculator doesn't give you the square root of 2. It gives you a floating point approximation of the square root of 2. So, maybe x is that approximation. We say that the absolute error between x and y is some number epsilon if the absolute value of the difference between them is less than or equal to epsilon. Oftentimes, we can't compute that number exactly, but we can say that the error is bounded by some number. In fact, usually you end up with, the computation that you would do to get epsilon, you do in floating point. And so you only have an approximate epsilon, so your error approximation has approximation error, which is why we use bounds instead of trying to get exact numbers. And it has relative error if you take that same difference but then divide by y and have that be less than epsilon. So one way to think about this is the first kind, absolute error, is the absolute difference between the two numbers, whereas the second error is percent difference between the two numbers. If something has 10% error, then you're going to have like 1.1 times or 0.9 times the original number, where if it had 0.1 absolute error, then the difference between them would be between negative 0.1 and 0.1. So note the difference. There's a percent error versus a number error. And we can write this down exactly, which is if we know that the error between x and y absolutely is bounded by epsilon, then there's some small number delta where x plus delta is y. And if there's relative error, then 1 plus delta times x is y. So note, the first kind leads to an addition, and the second kind leads to a multiplication. So this is what I mean by multiplicative and additive error. When we're to do a little bit of an analysis later using additive and multiplicative error, and you'll see that relative error comes up a lot. Yes, the slides will be posted after the lecture. And the recording will also be posted online. So for reasons, when the floating point standard was designed, relative error was the most important thing. So floating point prioritizes minimizing relative error. And this is for good reason. If we're doing a calculation and our numbers are in the billions, a difference of 1 kind of doesn't matter. If we're off by 1, that's not really going to affect our computation. If we're doing, a computation where numbers are on the order of 1, 2, or 3, an error of 1 is astronomical, right? If your number is 1 and you have an error of 1, your entire number is basically error. So relative error deals with this problem. You're not dealing with this problem where if you have a huge number, small number is considered small, like 1s and 2 error is bad. Anyway, I think it makes sense. But relative error is just kind of a better error to use, and so it's the error that we use almost exclusively. So again, when the floating point um, when the floating point standard was designed, um, it was chosen that floating point numbers would approximate real numbers with the same relative error across its entire range. So there is a biggest possible floating point number that you can approximate and a smallest possible floating point number you can approximate. But across that entire range of what we call representable numbers, the relative error is essentially the same. Um, and like this is kind of an amazing decision on their part because it makes my life so much easier. And it's exactly why we can always think about floating point numbers as um, in scientific notation, because scientific notation does the same thing. You care about digits of precision in the mantissa, but your exponent is always accurate. It's always exact. And that fact is exactly the statement that the relative error is chosen to be equal across the entire range of representable things. Um, in fact, this relative error is so important that we give it its own name. In fact, the smallest relative error that is achievable with floating point is called a machine epsilon. Um, and for 32-bit, it's roughly 10 to the minus 7, and for 64-bit, it's roughly 10 to the minus 16. When designing computer algorithms as a computational, well, when I do computational mathematics, my goal is to get every single algorithm I do to be roughly machine epsilon accurate. Um, so 10 to the minus 16 is kind of the gold standard, the best you can possibly hope for. So if you can reach it, you're fine. Um, yeah. Yeah. Um, what I mean is this. So there's this thing called the rounding function, which is basically if I have a real number, I round it to be a floating point number. And the floating point standard is designed to make this rounding function have machine epsilon relative error no matter where, well, as long as it's representable. So if it's between like 10 to the 38th and negative 10 to the 38th for 32-bit numbers, the rounding function will be a machine epsilon relative error function, no matter where. If they hadn't made this decision, it would be possible that if you had a number that was twice as big, the relative error could have also doubled, but it doesn't. If you round a number, a number that's between 0 and 1, and you round a number that's between 1,000 and 2,000, the relative error will be basically the same. Does that make sense? Does that answer your question? Awesome. Yeah, and so these are the representable ranges, by the way. I know I had them somewhere. So it's 10 to the 38th roughly for 32-bit and 10 to the 308th for 64-bit numbers, which I have actually had to do a computation in this range, and it was terrible. This is the rounding function. It kind of doesn't exist, but it kind of does. It's more like a mathematical thing. It's like basically you take a real number and you just send it to whatever the closest floating point number available is. And so yeah, it turns out that because of the design decisions they made, the rounding function is always machine epsilon accurate for relative error. Um, so yeah, this is kind of this wonderful fact, and it makes our lives much easier. Um, now, whenever we have real numbers, there's like four things we want to do with them. And there are more than four things, but all the things can be built out of these four things almost. Um, you want to add them, you want to subtract them, you want to multiply them, and you want to divide them. We are not going to talk about the algorithms that are used to do these computations. because I don't know what they are. I don't know any mathematician who does know what they are. I know some computer scientists who know exactly how they're added and subtracted, but it doesn't really matter. What I can tell you is true is that all four of these floating point operations are accurate to within machine epsilon. Uh, and so, from a mathematical point of view, we actually just take this, what's called axiomatically. We just assume that that is true. We assume that all of these are accurate to within machine epsilon, and we don't really worry about anything else. However, there is still error. So we can't call them plus, minus, multiply, and divide. We have to call them floating point addition, floating point subtraction, floating point multiplication, and floating point division. And so we give them their own little symbols, this O plus, O minus, O times, and O slash. And we just kind of assume all of them work. Um, now unfortunately, I don't really have too much time to go into much of the other things that we can do with these four fundamental operations, but I do, and also just floating point approximation in general. But I did just kind of want to go into um, some stuff that we care about. The most important thing we care about with all this floating point computation stuff is something called stability. Now, when I was learning math and I was learning computational math, the term stable would kind of just be thrown around without ever being like formally defined. And that is kind of because stability is a word that has a lot of different meanings depending on the context. But in general, we say that some computation is stable if small errors in the input lead to small errors in the output. Now, for anyone who's studied a field of mathematics called real analysis, or anyone who's taken a calculus class with a particularly cool teacher, this might be ringing alarm bells for a concept called continuity. And it turns out stability and continuity are basically the same thing, which is kind of a wild, well, it's kind of an obvious thing in some senses, but also a wild thing. Um, like, if you look at the function that maps your input data to your output data, in some sense, stability and the stability of that map and the continuity of that map are like the same thing. Um, so that's fun, as we say. But yes. And like whenever we write an algorithm, we want the algorithm to be stable. Um, so let's look at a pretty easy, simple little algorithm and study whether or not it's stable. So I have this map. It takes in four numbers, and these are real numbers. These are perfect numbers. We're just doing this all in beautiful math land. So it takes in four numbers: x1, y1, x2, y2, and it maps those four numbers to this value right here, this x1, x2 plus y1, y2. Again, this map is perfect. We're assuming that it has perfect accuracy. It's just using like real number multiplication. We don't have to worry about any of the floating point consequences. Except we do want to do this on a computer. So we have to replace the multiplication and the addition with floating point multiplication and floating point addition. And implicitly, we have to round these numbers to floating point numbers. So I have a question. Do you think this algorithm, this method of computing this product and sum is going to be stable or unstable? I have two guesses. I want more guesses if possible. People are being very meta about this. I mean, come on, guys, come on. It's just multiplying and adding. What could possibly go wrong? Okay, apparently I cannot trick people. Um, so this algorithm is going to turn out to be unstable. And like that is, I think, kind of a wild statement. Literally the action of multiplying two sets of numbers and then adding them can be an unstable computation. Wild. Um, so let's look at this. I intentionally wrote this just absolutely awful thing to show you what some of these computations can look like if you don't bean count carefully. Um, but what you can do is say, okay, I'm going to round x1 to a floating point number. That's going to have relative error. Relative error is multiplicative error. So I can sum up this error by just multiplying that number by 1 plus some small number. I can do the same thing for x2, the same thing for y1, the same thing for y2. Okay, but now I'm multiplying those two numbers, and the act of multiplying those two numbers also has some error. So I have to add some relative error for the multiplication. But then I'm adding those two numbers, and that adding two numbers has error. So I have to multiply, etc., etc. Right? You get these like compounding errors. But if you do all the algebra, you end up just getting this is actually a different epsilon 1 than the original one, but like you just get some error times this product plus some error times this product, right? You just multiply everything out, you group all the errors together, and you get this. And note, these are actual real numbers and actual addition. All of the error has been baked into this multiplicative term here. If we didn't have floating point with its beautiful relative error convention, we basically would have to use something like the top thing or worse. But because of floating point and its great design, we only have to analyze this much simpler error expression. Thank goodness for floating point. And so, relative error, we can use the formula I talked about earlier. Uh, and this is actually going to be the formula for the relative error, because this here is my approximation, the thing on the right, and the thing on the left is our actual true value. So Borb asked why floating point design simplifies the math, and the answer is because all of it is multiplicative error, and multiplicative error multiplies. But if at any point in this we had additive error, if any point in this we had absolute error instead of relative error, we would have multiplication and addition, and so we would have to do distribution. Here, we can just clump all the 1 plus epsilon multiplies together into one giant 1 plus epsilon. Whereas if we had at any point had absolute error, we would have had to do even more algebra. So that's why the all relative error all the time convention is so good. Yes, and so it turns out the relative error can be expressed as this thing on the right. We have whatever our error is times the first product plus whatever our error is times the second product divided by their sum. Can anyone point out a potential issue here? Yes, as Armand said, the bottom could be 0. Now, for reasons that I can't get into because of the level of math that I said this talk was for, this is not necessarily an issue. what we can do is we can basically say, okay, yes, if we're dividing by 0, this is a problem. So let's just not divide by 0. But maybe we get very close to dividing by 0, and we can analyze the error in that case. And so it turns out that would be all fine if these two relative errors on top were exactly the same. Because if these two errors here were exactly the same, we could factor them out, and then the top and bottom would cancel, and we would just be left with some error. And that actually would show us that the relative error was small, and that would be good. However, these two errors, nowhere did we say that they are equal. In fact, we kind of assume that they're basically random. And the probability that two random numbers are going to be equal is essentially 0. Actually, it is literally 0, but for the purposes of this talk, it's essentially 0. And so we basically cannot factor these epsilons out. And so if you only know algebra, your ability to analyze this kind of stops here. But there is some tricks you can do to get an intuition about it, and you also can do some other analysis, which again I'm not going to go into for both time and difficulty reasons. But you can either reason or prove that the relative error can potentially be infinite. Basically because of this division by 0. If you look at the function 1 over x, as x gets very small, the number blows up to infinity. And it's possible to basically get a 1 over x type behavior where the error blows up to infinity. And so the relative error can get huge. Now, this is kind of true in a theoretical sense that it's potentially infinite. Well, actually, and that is true. The relative error can be infinite, but the absolute error can't. It's one of these weird things where the absolute error, can never be infinite, but the relative error can, because you're dividing by 0, basically. And so yes, this algorithm is not stable. The relative error can just balloon out of proportion. And so, you might ask, like, okay, why does that matter? Well, if you've ever computed the dot product in Roblox, this is the dot product. This is actually the two-dimensional dot product, the vector 2 dot product, but it is also, the vector 3 dot product is also unstable. And it basically, the instability happens if your two vectors are at roughly 90 degrees from each other. And so, this is something you genuinely do have to avoid. If you're taking a lot of dot products in a computation, you should be scared that it might be unstable. And you should be justifiably scared that it might be unstable because there are actual practical cases where it is not. Yes. Another thing you can run into, which we don't have much time to talk about, and therefore I did not write much on, is this thing called catastrophic cancellation, which is where you subtract two numbers that are very, very close to each other. If you do this, what will happen is, again, you can write this multiplicative error thing, and if you do the algebra and you subtract these two numbers, you're left with this error difference here. But this is basically all error. It's all, error times x. And so this is called catastrophic cancellation, which happens when you subtract two numbers that are very close to each other. And this also can lead to some issues. So if you're doing computations that require subtracting a lot of numbers that are very close, you have to worry about this. On Friday, we're going to be talking about numerical differentiation. And numerical differentiation, by definition, is basically going to be all subtracting very close numbers. So it's something that we're going to have to watch out for when we're doing that. So that is my time for today. Thank you all for coming. We're going to have this is kind of the most technical of any of the talks that we're going to talk about, but I wanted to start with it because it is also the most commonly interacted piece of this. It's a piece of this week of talks that you're going to most commonly interact with, and it will come up occasionally in all the other talks. So it's an important thing to study. So we have a list of the talks that are going to be happening this week. There's going to be one on polynomial approximation, one on spline approximation. I can't remember the other one. And then we're going to talk about numerical integration and differentiation. Yeah, so thank you all for coming and listening. And I'll be least squared. Thank you, least squared. So yes, tomorrow is polynomial approximation, then spline approximation, then least squared approximation, and then numerical integration and differentiation. So yeah, I'll take any questions you have. Thank you all so much for coming and listening. There's a question, is the main problem with catastrophic cancellation for differentiation that you don't want to know if it's positive or negative? No, so catastrophic cancellation won't. So catastrophic cancellation is infrequently a problem of sign as much as it is a problem of significant digits. So if you have two numbers with the same exponent, when you subtract them, it's basically like subtracting just, we can just forget the exponent and just subtract numbers like, like we would normally subtract numbers. And so if the two numbers share a lot of digits, then a lot of digits will zero out. And so you'll be left with like 0.000004, for instance, times your exponent. Well, okay. When we, in significant figures, what you have done is you've lost digits of precision because zero digits are meaningless for precision. And so basically, you will use the exponent to march the 4 back up to be your first number. But now, in doing that, when you march your 4 up, you're kind of dragging in digits from pure error. And so you might go from having, 13 meaningful digits to having 2 meaningful digits. And then everything after the first 2 digits is just error. And so this is what you run into with catastrophic cancellation. Yeah, you just absolutely destroy your error or your accuracy, I should say. I've never really run into a problem where the sign was wrong, but